Pleasure to have Ceren Kose from University of Georgia. Tell us about her work on symmetric unions and ribbon knots.
Thank you for the invitation. It's very nice to be here. So I'm going to talk about symmetric unions, a class of ribbon knots, and I would like to just show maybe like another way of studying or building slice knots and like what we know about them so far. Okay, so maybe I should have, but I will still give the basic definition. So we know that we say a knot, K is slice, if it bounds a ball, it bounds a smooth ball. If there exists a smooth embedding of the ball, properly embedded, such that not in this tree, maybe not in this tree. This is a three-dimensional, this is a four-dimensional property, and if we want to see them in four dimensions, in like 3 dimensions, a nice way to find the slice knot is through ribbon disks. And we say, let's say a disk or K is a ribbon knot if it bounds a disk, which is a disk with only ribbon singularities. Locally, it looks like 2 strands. It's just where the singularity, when we basically look at the preimage of the singularity, we will see 2 disjoint arcs, one of which will contain in the interior of the disk. And if our immersed disk in S3 has only this kind of singularities, then we call it a ribbon disk, and then the boundary of such a disk, we will call it a ribbon disk. Okay, let's see an example, maybe like a non-trivial example. Here's a ribbon disk with actually a boundary, so this D with the boundary, the square knot. So that actually arises a question, right? Then if now we have this like 3-dimensional property of a slice disk, because basically the fact that one of the preimages of this singularity is interior, that will allow us to get a neighborhood that is contained, that is completely contained in the disk, where we can actually push it up when we move to the 4th dimension, and it will give rise to a smoothly embedded disk where the boundary remains the same. So this actually implies ribbon is slice. Okay. So if we have a ribbon knot that is slice, and the converse is one of the most important and challenging open problems in knot theory. Okay, so I can draw ribbon disks, and then now I know that the boundary is a knot, but how it's just, as a knot theorist, I would like to get a knot construction that will always give rise to a slice knot, or at least a ribbon knot. Okay, then starting with this, we know that if you take any which knots are maybe slice or ribbon. Which knots are ribbon? Okay, clearly like any knots, any square knot in this one for any non-prime knot. K connected sum is mirror for any K. Yes. Because as you we can actually just like look at the core image here. And maybe push this in a in a trivial way, so that the ends are in the same region. Like now we can see that, like take the core. Oh, up, okay. Down. Like that. So here, this should follow. So now we can see that actually like this part of the picture. It's like the core of the ribbon disk. And now if we take the axis, symmetry axis of the K connected some mirror K, and maybe like spin the half, this core arc inside the board, we will actually obtain this disk. But now I can like, one thing I can do, like I can maybe grab a region and insert twists here. That's not gonna change the fact that the resulting surface is a ribbon disk. And as a diagram, I can see that twisting happening along here, that I can basically insert. We can insert vertical crossing here and still get a ribbon disk, because this will only correspond to putting a new putting like a twisted band here. And this construction generalizes by, and it's due to Kinoshita and Terasaka. But we say if a knot admits such a diagram, we say a symmetric union of a knot, that we assume that, let's say, we take any knot J, and we basically build a symmetric union of J as follows. Then so basically I take any random diagram, any diagram I want for J, and we connect summits with, is that large enough? Okay. So we take a diagram of J, and we take then its connected sum with its mirror, such that there exists an axis where the resulting diagram is symmetric across the reflection across that axis. And now it's basically any knot diagram where you can insert the twists along the symmetry axis. Any questions so far? So this is based, I mean, I'm basically generalizing, we're basically generalizing the above construction. Okay. And polynomial notation. So if we can, present a knot in that way, it will be called a symmetric union, and we will denote it as that way with this notation, where this J here represents the base knot we started with, but in the literature it's called the partial knot, and these will represents the half twists with sign. So for one, you corrected me on this in my thesis. It's not going to be this one. It's going to be this, yes, and -1. So the two will be.
Because you're looking horizontal.
Yes. Exactly. Okay.
But you're looking horizontally.
Okay.
So I mean, your boxes are going. Which way are your boxes going?
My boxes are going in the.
Yeah, the vertical. So
exactly. Sorry.
So you want your
this
one.
actually has to be like that.
Yeah.
Thank
so.
you.
So I would normally say what you have is -1. Personally, I would call that a +1.
This
I would
one?
call that a minus.
This one is minus? This one is plus now.
Well, if your thumb's going upwards.
Yes, but for the tangle, from the tangle location.
I mean, yeah, it depends on what your basis for the tangles are. Sure.
Okay.
Anyway.
Let's have it that way.
Yeah, as you're comfortable with it. Just however you have it. I mean, we can talk about.
No, I used to have it that way, and then I was corrected.
We can. I mean.
Okay.
There's. Yeah, we'll talk about that later. If you're using the standard.
Yes, I want to use the
Conway's
notation for the rational tangles.
Right. So there you're thinking of it as a rational tangle rather than just a sequence of twists.
Exactly, that's true. That's actually a very better way of saying. Maybe I can think of all these boxes, NIs, to be that I got this just like plain zero tangle.
But the point is, if you've got a vertical tangle, then the Conway would call that 1/2.
Yes.
I mean,
it's just the number of. It's just the number of recording it, because they're always going to be 1/, and so I can just write NI. It's just a notation.
Yeah.
Oh,
I'm just saying.
Inside I need to write 1/.
I mean, it just. I think right now just choose what you want to write.
Okay. Yeah, but okay. I mean, I'm just gonna write NI because it's shorter. But what it does is basically, because if we have these local tangles, that the starting diagram was just the connected sum, but now I'm basically taking this tangle and replace it with 1/NI, rational tangle, and that's very specific. Actually, it always have to be NI for this construction. I mean. You can flex it and maybe you still get a ribbon knot, but if you just choose it that way, you'll get a ribbon disk because of the similar idea of spinning this half of the diagram inside the board. Okay, so this. Okay, now this proves that. So this proves that the symmetric union is ribbon, and hence smoothly slice, and similar to slice ribbon conjecture, the converse of this also unknown. So we still don't have any obstruction for a ribbon not to admit a diagram like that. Let's see an example of this construction. So, I mean, I said that this knot construction is due to Kinoshita and Terasaka. So the Kinoshita and Terasaka knot is this symmetric union, and here it is. you can see the symmetry axis here. So this is, I'll just use KT to denote Kinoshita and Terasaka, and you can see the ball where we do the tangle replacement here, where the number is 2. So we can say that the Kinoshita Terasaka is, and then you can work it out to see that the partial knot will be the unknot. So this will be like symmetric union of the unknot with 2 twists. And that's also another way to show that KT is slice. Okay, so what are some connections? Okay, this is maybe. What are some connections? So we know that from Fox and Milner, the Alexander polynomial of if K is slice, we know that it's Alexander polynomial factor out as F, some like learned some polynomial, and it's F T inverse. Then an immediate corollary of this is that the determinant of a slice knot is always P squared, where P is some odd integer. So Kinoshita and Terasaka shows that if you have a symmetric union of any knots, and in that notation, if I don't write J, it doesn't matter. What is the? Oh, actually, I need to put it. Okay, where all these twist coefficients are even, then we actually recover this factor. It turns out to be the Alexander polynomial of the partial knot. But in general, so for any simu, the determinant of K is the square of the determinant of J. So if your slice knot actually admits a symmetric union diagram, you kind of recover these factors. What else do we know? Okay. Maybe as an application. So in 2017, so actually in 2016, those were the 2 knots with less than 12 crossings whose sliceness status were not known. We just, in that year, we didn't know whether they were sliced or not. And actually, Axel Seliger produced a symmetric union diagram for this knot to prove that it is sliced. And then we all know what to combine. Any questions so far? So here's one application that you can use this to show slices. So,
what is it? A symmetric union now?
I don't.
What was the name of the first teacher?
Seliger. Axel Seliger. Okay. So, like another way to build ribbon knots. Is that we can have these pieces. So normally we usually have a four manifold picture. I mean, we know the 4D picture of the ribbon knots where we get this like concordance to our knots. But this is like another way to maybe see it in 3D or in three dimensions, or like another combinatorial way to study it, like I mean ribbon disk. And by so Eiserman shows that, well, any ribbon disk can be composed by these pieces, right? And he shows that if K is ribbon by using this construction. If K is ribbon, then the determinant of K is 1 mod 8 by using Jones polynomial. So it's kind of like, because we already have this, but this result relies on Alexander polynomial, and there were no other techniques to show something similar to this. And I think in the literature, this is like the closest you can get to this determinant of K is a K-square for a slice knot. And but if you remember, the symmetric union construction, which is basically very similar to just like getting the spin disk of K connected to some mirror K and just like hitting vertical twists, or like, taking these kind of pieces and then replacing them, you can see that any such disk can only build by using these three pieces. And the converse is also true. So let me actually not write it here. So maybe a new definition. Symmetric. Ribbon disk is the one that is only built like that. Only with these three pieces, and the converse is also true. That if I build a random like a ribbon disk by only using these three types of pieces, the boundary will admit a symmetric union diagram. Then the question is that you can ask, like, whether is there a ribbon disk which is not symmetric. This is still not known. And Acheto gives an infinite family of ribbon knots. There exists Kn such that its ribbon number, where the ribbon number is just the minimum number of like the ribbon singularities spanning among the disk. Ribbon disk spinning Kn, where the ribbon disk is fixed. The ribbon number is always 2, but maybe the symmetric ribbon number is larger than n. Then this number is like the minimum number of singularities among the symmetric ribbon disks spanning K. But it still does not answer this question, but it like provides a very like strong evidence that we probably have some like ribbon disks that just that there is no isotopy to
So
get rid of these two pieces.
Being that, like you have a presentation, a ribbon disk where you see these two ribbon intersections, but if you need but I guess in this case you can see that you're isotoping that ribbon disk into a symmetric presentation, which causes those intersections.
Exactly. So whenever you want to do that, whenever you take this disk and if you want to put it in the symmetric union representation, it just introduces non-trivial ribbon singularities. Among the symmetric ribbon disks, because it's already trivial among ribbon disks.
Is that the proof? Is it diagrammatic, or does it rely on something?
No, that actually relies on studying like the Hagar genus of the double branch cover. It's not diagrammatic. Yeah. But we have smaller examples, like I think there is now only 15 like ribbon knots with less than 12 crossings that we don't know where they're symmetric union or not. 15 prime ribbon knots, and some of them are here, and these are the composite ones. And we have this ribbon disk actually where these parameters generate all of these knots that we don't know whether none of them are is known to be symmetric union. But we also don't know like whether this disk, like which still there is no proof whether this disk is symmetric or not. Because this disk actually generates already like enough number of candidates to prove that that's not true. To sort of like maybe disprove this. Okay, so this is like an invariant to. This is maybe like an invariant to study symmetric unions, or like in this case, this is a symmetric ribbon disk. So now I want to introduce like a new invariant, which is the minimal twisting number. Let's say K is a symmetric union. Some twist, then the minimal twisting number is basically the minimum number of the twist regions to obtain K in a among the symmetric union diagrams of K. So I mean certain things like if it is 0, then it's just clearly the square knot. And an example of a 1 with twisting number 1 is the Stevedore's knot, or in fact, like we can take any Preston knots of this one. And Tanaka also uses Jones polynomial to give the first example of the one that is first example of knots that has 2. But this this result relies on the very careful study of the Jones polynomial, but it doesn't immediately give you a structure to produce an infinite family. So now I can state my results. So now I will characterize the symmetric unions that have twist number 1 who are two-bridge composites and Montesinos. And hence we will get infinite families of ribbon knots that cannot have any twisting number 1. A. That's independent with Tanaka. Okay, and the rest are my results. Oh, I'll write them down.
It's theorem A, B, C, D.
Yes.
With attribution.
So A is Tanaka and I independently with B, C, R. So K, B, A, symmetric union. With twist number 1. Then A will tell us if K is composite. Then K decomposes as some non-trivial knot and its mirror, and some other symmetric union. One. And B is if K is 2 bridge. Then K is so from like Kesson and Gordon, we already know that there are like 3 families of 2 bridge knots. They just have like this particular Conway notation for each of them. And Lamb already showed that they were all symmetric union, like he already produced a diagram for those. And in the first one, in Kesson and Gordon family, which is this case, which is the knots in this one, the twist number was already 1, so we already know that they were they had 1. But for the other 2 families, the diagrams he had 2 twist regions, and now this shows that like those diagrams were minimal. And here we can also say that like the knot we started with is also some other like 2 bridge knot where the coefficients are determined by the coefficients of the knot you started with. And the interesting thing is that this is unique. Q is here. You can also determine uniquely, and these knots are basically like the first infinite families of 2 bridge knots where the partial knot is unique.
You know, then the other ribbon or the other slice 2 bridge knots have twist number 2.
Yes.
So Q is, there's a formula for Q in terms of D and T?
I don't remember that, but yes, there is a way to build this T by using Q. And even though you have, for the two bridge knots, even though like you have like Q times Q prime 1 mod P, it's kind of equivalence, and that still works. So yes, it's unique. I just gave a very complicated way. And if K is Montesinos, then K is exactly how you would think K is. It's basically start with some partial, some like angles, some rational tangles, and like basically have as many as you want. And along the way, just have some like a vertical one, and then just like mirror symmetry the rest.
So that's just set up immediately as.
No, that's not the setup.
But I mean, the point is like once you see it in that form, that tells you, it gives you a basically hands you the symmetric gradient.
Yeah. Okay. I mean exactly. So if the Montesinos knot is in this form, yes, it's already a symmetric union. But like
you have to show that.
Yes, this basically tells me that these are the only ones that you can obtain with 1 twist regions. For the others, you need more. And if you like, for instance, this one is a Montesinos. More importantly, like one nice thing about this, we know that for the Montesinos knots, like the homeomorphism type of the double branch cover, like determines the type of the Montesinos knot. So I can just like rely on the earlier invariant, and here like the earlier invariant gives you kind of an obstruction for like a ribbon Montesinos knot to admit a symmetric union with 1 twist region, because it always has to be in this form. And here, I think this is a Montesinos knot. I need to check my notes, but this is something like 9/2. So at least we can partially say that if this has twist number larger than 2.
At least.
Hmm?
At least.
At least two. And the other thing is that K is never amphichiral. I think these are all very interesting because all of them were like your first, it is for the first three, they were like your first immediate examples of ribbon knots, and they were the only ones. Like we just don't have a lot of flexibility in this construction, it turns out.
I mean, with the two bridge case, I mean, is it really just when n equals 1 in the Montesinos case?
Exactly. And yes, n has to be 1 in that case. And I will explain that. And like amphichirality too is like you already start with something amphichiral and you are doing this like, I mean, when I look at the previous works or the computations that kind of like uses these families, that you can immediately see in these examples, like in these examples that for instance, most of the quantum invariants like the Coulomb homology is just do not respect this amphichirality condition. So that was kind of my intuition to maybe that's K is probably never amphichiral. And that turned out to be the case.
Other amphichiral symmetric unions
Yes.
are just
Of course.
Oh.
I mean, you can even build it yourself, right? You choose the diagram of J in a, like, you start with an amphichiral knot, and then you use like maybe that kind of symmetry where you have two twist regions, like you put n twist and then negative n twist, and then arrange it in a way that you can use like pi rotation to take the knot diagram to its inverse.
Is there a minimal twist? Like what's the minimal twist number you can achieve for such?
Two. You can do it with two. There are some examples with two. In fact, like some of the Kananobu knots. I think, I mean, like even Kananobu says like the Kananobu knots are amphichiral if and only if like the PQ coefficient is like P1 minus Q. And that's exactly what I'm like describing in just the rotation. So here also you can like, and here then the partial knot you started with is just like the connected sum of these two bridge knots. Maybe I can, in the remaining time, I can like briefly talk about the ideas that goes into it. So I will start with B and C because they kind of they follow the same line. So suppose this is my like a schematic picture of my knots. So this already gives me like a nice decomposition, like a nice like a tangle decomposition among, if I like focus on these spheres. And then if I like if we consider the double branch cover, that will also give a like a decomposition of the double branch cover among like a torus decomposition of the double branch cover. So I can think of like maybe, let's say this piece Y is a double branch cover of this angle. And then all of these spheres will live to some torus. But if this is Y, this is just Y with the positive orientation. Sorry, negative orientation. And this space lives to something called the cable space, where the cable space is a cipher fiber space along over an annulus with one coefficient, with one singularity of coefficient 1 over n.
So basically the rest is for P, for instance. Now I know that sigma K is a length space, right? Then this T has to be compressible. But because of the symmetry here, I mean, if this part is not compressible, this part is not going to be compressible too. So I know that here Y has to be a solid torus. Then this tangle is a rational tangle, and then the rest is basically getting the Seifert vibration description using this tangle. And we know that then this gives it like a Seifert vibration for the double branch cover, but we know that that's the length space, so one of these fibers have to be trivial because Seifert length spaces can have at most two singular vibrations. Then if this is trivial, then I know that the knot I started with is trivial, like it's the unknot. But remember the determinant case, like then the determinant has to be 1, but the only to which not be determinant one is the unknot. So we kind of rule out that case. And the other case, then it's like 1 over n is trivial. That's why n is 1. N is 1, and then the rest is just like playing with the Seifert coefficients to show that it actually corresponds to this particular length space. Any question? And for part C, it's kind of now I know that it's a Seifert fiber space, but we already rule out the case where this T was incompressible, so it must be compressible, and we know that for the Seifert fiber surfaces who are also rational homology spheres, any incompressible torus can be isotoped to be vertical. Then it should co-bond Seifert fiber spaces on either side. That's why then you get like some Seifert vibration on this part, which will give us this kind of tangle decomposition. Then again, that's why like we have all these conditions. I'm gonna let any question? How much time do I have?
About another
Huh?
10, 15 minutes.
Oh wow! Okay, I have a lot.
5, I guess, technically, probably.
Okay.
Something like that.
So B and C are kind of like, I think, like straightforward once you see this picture. And maybe I should, I mean, this picture is nice because this is like the same sphere like the Conway took when he basically mutates the sphere in the Kinoshita and Terasaka diagram to get the Conway knot. So I find it useful. So the other A and D kind of like requires one more property that was maybe called like mirror symmetric property of symmetric unions, that if I consider the mirror of a symmetric union, what?
Mirror symmetry.
Mirror.
It's like a homology theory of this.
Actually, when I give this talk, I think there were some like algebraic geometry. When I gave a similar talk at UGA, there were some different mirror symmetry algebraic geometry in the room, and they apparently got very confused. But this is not like the symmetry that kind of preserves the orientation of history. So that's why I want to point out that this is like kind of reversing the orientation, so it's the mirror symmetric. Okay, so suppose K again is some like symmetric union, but now we can see that if you take the mirror of K, like it's just gonna switch the crossings, so I get the mirror of everything. But actually, the choice that I have here in the union does not matter. Like I can just like rotate the diagram. So this is actually, this is the basically kind of like the same symmetric union frame, but now instead of putting n-twist, you put negative n-twist. Okay, so maybe I'll say it that way. Negative k is the union d negative n. Okay. Then for part B, then if then we basically have a diagram where this thing happening, right? Like we basically insert a crossing and a negative and crossing, and for some reason, like you get the same knot, which seems very unlikely, as long as you're not inserting it in a non-trivial way. Well, in that case, it turned out to be. Maybe it's, there's some cases that you can get same knot. Okay, here then we can also like see that you can also get the double branch cover as a filling now. Like instead of this picture, now I will have a different picture for the double branch cover, but it's still quite the same. Now I'm just like looking at the tangle box. So remember what we've done to construct K. We started with this tangle, and then we replace it with some entangle. Then suppose I call this ball B, and let's say X is the exterior of B in S3. Then suppose X tilde is double branch cover of X, or along with the tangle that will be that will remain X K intersection. It's like X, some like tree manifold with torus boundary, right? But then when we do this, this basically corresponds to so here at the beginning I have the double branch cover of J connect with some J, and then this tangle replacement corresponds to a Montesinos trait, where we actually do 1/n surgery on some knot, like whatever the lift of the arc here. But you can also see it, this is just for the notation, or I mean, we can also view it as like 1/n the infilling of the double branch cover of the tangle here, which is like shorter. Okay. So, okay, I mean, if we go back to this picture here, so we have like two Dane fillings. One of them with 1/n coefficient, and then the other one is with 1/n coefficient. And the scenario should be that they have to be homeomorphic by an orientation preserving homeomorphism. But if you ever heard about like cosmetic surgery conjecture, like it rarely happens. I mean, for S3, the conjecture states that it never happens. I don't know for a general case what are the conditions, but
you will, yeah, you want to, the cosmetic, this is the, you're doing, you're getting the oppositely oriented guy.
no, this is, no, because K is amphichiral now,
Oh,
they're actually orientation preserving.
well, it's supposed to be an orient.
Yes, that's why this is not going to work. But one way to see that is like going back to this picture now. This is incompressible. This is incompressible. We already argued that. So this is actually, this picture gives like a kind of like not the entire JSJ decomposition, but it's like this piece has to be a JSJ piece for this manifold. And now we can like study the JSJ decomposition of that manifold and then this manifold, and we will have this piece. And then if there was an orientation preserving homeomorphism taking like this piece to C negative n, you can see that that's just like, no, that's never the case for cable spaces. I think the part A is maybe the most promising one to find counterexamples or counterexamples for the symmetric union ribbon question. Because we really don't have okay. I mean, I will describe the family now, and I think you will see it. So okay, let's say so we have immediately we see these two types, right? One of them is again like in the one of the square knot form. So any such knot is like trivially symmetric union, and then the other one is that if I take two symmetric unions and then basically like stop them together, then the remaining, like we can arrange the diagram, like I mean we can find a diagram for these composite knots. Of course, and not sure. But there is another ribbon knots, like another way of constructing composite ribbon knots that do not fit into these two types. So suppose I take a knot K, and then I find another, sorry, I take two knots that are ribbon concordant to each other, then they're connected somewhere. The connected sum of one of them and the mirror of the other one will be ribbon. And if either of them is non-slice, I mean the other one is also not going to be non-slice or ribbon, like this is not going to be, this is a such knot if K1 is not ribbon, it's not going to be in type 2, right? Maybe an example. This is not 810. Remember, I had the picture before that the triple connected sum 810 was one of them. Anyway, so you can actually just look at this concordance, and it will give you a concordance between 810 to 31, and you get like 31. Let me type that later. So this basically tells us that like triple connected sum 810 is ribbon, but not of type 1 or type 2. So the interesting thing is that for these families, there's no example of symmetric union diagram. So far they are sort of considered to be like the strongest candidates if you want to find ribbon knots that are not symmetric. And this knot is actually the smallest among them, and also 8, 11, like with 11 crossings. So here, at least in part A, Tanaka and I independently show that these knots will have twist number at least 2. And I will now briefly describe my proof, but also there is like a little thing that goes into my work that you don't find it in Tanaka's work. It sort of like gives a general picture for any twist number. So yes, actually, let me start with that. Okay, first the idea. So here we will again, I will again use the double branch cover because if a knot is composite, then it's like sort of characterized by a decomposing sphere in a tree. But you can basically like lift this decomposing sphere in the double branch cover, and you will see an essential sphere in the double branch cover. So, and actually this is a famous theorem of Wolfhausen that if K is composite, then the double branch coverage is reducible, which follows actually as a corollary of this, like the double branch cover detects the unknot result. But it turns out that the converse is also true by Kim and Tollefson. If I write KT again, it's not Kinoshita and Terasaka. Anyway, but this is nice. Like if you want to study composite knots, if you want to show if something is composite or not, you can also, another way to look at this double branch cover. It's reducible or not. Okay. So one thing that we can show in a full generality, not just for the twisting number 1K, if K, suppose K is not of type 1 nor type 2, then this manifold that we were filling to obtain the double branch cover is irreducible. Of course,
To do that, you'll need to turn off airplane mode.
Yeah, I can't prove that one without.
No,
Unless you turn off their. That's like a proof checker right there.
yes. So maybe a little notes here. Like it's important to note that like this X tilde double. In general, like it's just not gonna be a manifold with a torus boundary. Like it will have a multiple boundary components, each of which is a torus. But here we have to make a choice that X tilde was built using a minimal diagram, which is basically like the like I used to build this manifold by a symmetric union of K, where the twist number is actually the twist, where the minimal twist number is recognized. Like
Yeah,
that.
X, you're starting with the assumption that you've got twist number 1.
Here, actually, for this lemma, it doesn't matter whether
In general,
this is true in general. Like in that case, I will have multiple boundary components, and now we're.
union.
So this is, I think, interesting because it's basically if you're not in this like obviously symmetric union composite knot form, like the double branch cover is not obtained. It should be obtained by filling an irreducible manifold, and it will be irreducible, which is
Just the hypothesis on K is that it's a symmetric union.
Oh yes. Sorry. Okay. Then like. Then, as I explained, for like one boundary component is like you have a reducible manifold and you fill it and you get a reducible manifold. That's like rarely happens, and that's a theorem of coordinate here. So suppose M is a 3 manifold with boundary a torus. And if we have 2 fillings that are reducible, I need to say this is an oriented and irreducible. then the distance between these two slopes is 1. So sketch proof of so for A, then if K is composite, right, then the double branch cover is reducible. But remember, this was x tilde n, 1 over n, sorry. If K is a symmetric union with 1 to this region. But then we observe that the mirror of K will also be a symmetric union with negative n coefficient. And now we actually obtain two reducible fillings of x tilde, because now this filling will correspond to the double branch cover of the mirror. And if one of them is reducible, the other one is also reducible. So, but then we show that for any n, this is 2 times n, which is like never 1, or never small from 1. I mean, only when n is 0. So that's kind of concludes term A. Okay, then I can stop.
All right, well, thank you very much.